Question 5 concerns the 1969 moon landing. The lunar module separated from the command module above the surface of the moon when travelling at a horizontal speed of 2040 meters per second. In order to descend to the moon's surface, the lunar module needed to reduce its speed using its rocket. This is shown in a diagram. In A Part 1, the average thrust from the rocket is 30 kilonewtons, and the mass of the module is 15100 kilograms. We need to find the horizontal deceleration of the module. Well, acceleration is force over mass, and we have a force of 30 kilonewtons over 15100 kilograms, giving an acceleration or deceleration of 1.99 meters per second squared. This is close enough to 2 meters per second squared to one significant figure, the same as we have our force 2. In part 2, we need to find the time taken for the lunar module to slow to the required horizontal velocity of 150 meters per second. We can assume the mass remains constant. Well, we can use final speed is equal to initial speed plus acceleration times time, and rearranging for the time, putting in the values, here using an acceleration of minus 1.99 meters per second, which is our deceleration, and this comes out at 950 seconds. In B, the rocket was then used to control the velocity of descent, so the lunar module descended vertically with a constant velocity, as shown in this diagram, this representing the module. Due to the use of fuel during the previous deceleration, the mass has fallen by 53%. The moon's surface is down. The acceleration due to gravity near the moon's surface, 1.61 meters per second squared. In part 1, we need to draw force vectors on the diagram to show the forces acting on the lunar module at this time. Where we'll have the weight acting down and the thrust from the rocket acting up. In part 2, we need to find the thrust force needed to maintain a constant vertical downwards velocity. Well, for this, weight must equal thrust. Weight is mass times gravitational field strength, and we have 47% of what the original mass was at 15100 kilograms times the acceleration due to gravity given in the question at 1.61 meters per second squared, giving a value of 11426 newtons, or 11,000 newtons to two significant figures. In C, when the lunar module was 1.2 meters from the lunar surface, the rocket was switched off. At this point, the vertical velocity was 0.8 meters per second. We need to find the velocity at which the lunar module reached the lunar surface. Well, for this we can use v squared equals u squared plus 2as, and we want v, which was equal to the initial speed of 0.8 meters per second downwards. The acceleration is still 1.61 meters per second squared, and we have a distance to travel of 1.2 meters. That comes out at 4.504 meters squared second to the minus 2. Square rooting gives v at 2.1 meters per second.